Hello, this is Math 1120 coming to you from the College of Tage, and this lecture is entitled Probability Theorems and Applications. So today we're going to talk about one of the things is the addition rule for disjoint events. So two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. And here is the addition rule for disjoint events. If E and F are disjoint or mutually exclusive events, then the probability of E or F, and in math class you would call this E union F, is equal to the probability of E plus the probability of F. So we're going to use this now. So we often draw pictures of events using Venn diagrams. These pictures represent events as circles enclosed in a rectangle. The rectangle represents a sample space, and each circle represents an event. For example, suppose we randomly select a chip from a bag where each chip in the bag is labeled 0 through 9, the integers, and let E represent the event that you choose a number less than or equal to 2, and F represent the event, choose a number greater than or equal to 8. The events are disjoint, and that's shown in this figure. You see E and F have nothing in common. And notice that there is some stuff that's outside of both E and F in this example. So if we wanted to use the addition rule for disjoint events, we would say that the probability of E is equal to the number of things in E divided by the number of things in the sample space. So that would be 0.3. The probability of F similarly is 2 out of 10. But the probability of E or F is going to be, you add those two numbers together and you get 0.5. Now this is only true for disjoint events. The addition rule for disjoint events can be extended to more than two disjoint events, however. So if you have probability of E or F or G or dot 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 just keeps on going, but that's the same thing as adding up the probabilities of E plus the probability of S plus probabilities of L plus dot dot dot. But this is only for disjoint events. Okay, so let's look at applying these to this one. Now we have a distribution here. And so they're talking about the number of rooms in a housing unit and the probability of those rooms. And I think I may be blocking some things down here, but we'll see those numbers later. So this is distribution. So first of all, we have to verify this is a probability model. So we have to check to see that all these numbers are between 0 and 1. And if my face is showing there, just trust me that those numbers do all add up to 0 and 1. Although if I ever ask you to verify something as a probability model and just give you the numbers, you would add them up. So they do all add up to 1, and they're all between 0 and 1 inclusive. So then I can ask you a question, what is the probability of randomly selecting a house that has 2 or 3 units? Well, you see either it has 2 or either it has 3. Those are disjoint events. It has one or the other, and so you add those two probabilities and you get 0.125. Here's another example. What's the probability of random housing selecting 1, 2, or 3? Well, either you have 1, either have 2, or either you have 3. If you have 1, you don't have the other. So we just add up those probabilities and we get this. Note that Excel can add up these probabilities very quickly for you. Now we're going to talk about the general rule, though, because all sets aren't disjoint. So this rule, the general rule, says for any two events E and F, the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. So you add the two together, but then you subtract off the probability where they overlap. And an example of this could be found from the dice game that we talked about last time in the VCN lecture. And here's maybe a prettier picture of that dice game. But you see these are still the blue die and the red die, or here you would talk about these being the first die or the second die. And this is all of the possibilities that you can get. Okay, so what we're talking about here is let E and F be, let E be the first die is 2, and F is the sum of the die is less than or equal to 5. Now we're to find the probability of E or F using the general addition rule. Now you see The first die could be a 2, and that happens in this row right here. The first die is a 2, but then you say the sum is less than or equal to 5. So you see, I would have situations where it would be the sum is less than or equal to 5 would be all of those numbers that are where they add up to less than or equal to 5. So you see there is some overlap here. So we can do those calculations, and what we'll find is we take the probability of E, which is 6 over 36, plus the probability of F, which is 10 over 36, but we have to subtract off where they overlap, which is 3 over 36. So you have to do those fractions, and you get 13 over 36. This is very important, and I certainly will ask you questions about this as we go forward. We're also going to discuss in this lecture the probability of an event using the complement rule. And the complement rule says, and the complement in this class is denoted as E complement, and that is all the outcomes in the sample space that are not in S. So it's everything that's in the universal set but not in S. Okay, so that's what we have. That's the definition of the complement event, and the notation is going to be E, writing C like an exponent. And here's a picture of that. So if set E is everything inside the circle, E's complement is everything outside the circle, and that's here. Now this is what the complement rule says then. If E represents any event, then E complement, and E complement represents complement B, then the probability of E complement is equal to 1 minus the probability of E, because you see either E happens or it doesn't happen. So the probability of their union is the probability of the whole space, which we know adds up to 1. There also are important applications of this. And let's illustrate it. Okay, so we know that 31.6%, according to this data, of American households own a dog. What is the probability that a randomly selected household does not own a dog? Well, so the probability does not own a dog is equal to 1 minus the probability you own a dog, and you do the calculation, you get 0.684. Let's look at a broader example. This data represents the travel time for work of residents of Hartford County, Connecticut. So this is a frequency chart. So you see you can have the data given to you in different representations. So the question is, what is the probability that a randomly selected resident has a travel time of 90 or more minutes? Well, 90 or more minutes are way down here at the bottom. And so what we can do, and what we will do, is find the probability of all these others and subtract it from 1. And that's what happens here. So you can use Excel, but there are a total of, if you add it all up, the entire column, these frequencies, you get almost 400,000 residents. And the probability that they will have a commute time of 90 or more minutes is the number here, which is hiding behind my face, but that is 4895. So you take the ratio of those two numbers, and that is a little better than 1%. Here's another thing based on the same table. Compute the probability that a randomly selected resident will have a commute time less than 90. Well, less than 90 is going to be 1 minus 90 or more. And 90 or more, it will be found to be this. So 1 minus that gives you this number. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and each other. God bless you all.